Okay, good evening, everyone. And the outset, let me thank Praveen for this wonderful opportunity, for the invitation and the hospitality. And I'm really glad to give this talk here. And the title is Structure Preserving Finite Volume Scheme for the Barotropic Euler System. And this is based on some joint works with some previous PhD students whose name you can see there. And as mentioned by Praveen, this structure preserving is basically maintaining some properties of the PDEs, underlying PDEs, here in this case is the barotropic Euler system, at the numerical level. So here we are going to use a finite volume setting, and we try to maintain some of the key features of this system. So I will be focusing on basically three structures here. One is the positivity of rho, because it's a barotropic Euler system. The only variable where we have to maintain the positivity is rho. And we want to maintain the positivity of the density, the rho. And the other quantity which we want to have is the energy. So we want to have a numerical scheme which is energy stable. And the third is what we call a low Mach number limit. This is when a parameter present in this equation, namely the Mach number, that goes to 0. These equations have a limiting behavior, and that behavior we want to respect at the discrete level. So these are the three aims behind this work. And here is a brief outline of this talk. So we present this zero Mach number limit, what exactly it is. And so we introduce the equation set, the limit, and a technique which we call a velocity stabilization that is at the core of this discretization. And once we do that, I go to the numerical approximation strategy that is further divided into these sections, like what is the mesh and how the unknowns are stored, and the discretization operator, the convective fluxes, and the other differential operators. Then we introduce our final numerical scheme, then its attributes like the energy stability, some weak consistency, and some convergence. And finally, the consistency with this zero Mach number limit. And I present some numerical results, and we conclude with some summary of this. So here is the equations. So I start with compressible Euler equations parameterized by an epsilon, which is the Mach number that appears here as 1 over epsilon square. So here, this first equation is the conservation of mass. Second one is the conservation of momentum. And epsilon here is what is called the reference Mach number, which measures how compressible the fluid is. And this rho epsilon is the density, and u epsilon is the velocity of the fluid, and p epsilon is the pressure, which we assume it to be a simple barotropic law. So P is given by rho to the power of gamma, and this gamma is a constant for the gas that is always greater than or equal to 1. So this is the system, and I have the initial and boundary conditions. So I assume this solid wall, this no flux boundary condition, and the initial condition for rho and the u are given to us. So this is the equation. Now I make a definition of what is called ill-prepared initial data. So that is given like this. So basically we assume that this initial velocity is bounded in L2, and this rho naught epsilon minus 1 in L infinity is like C epsilon. So this is what is called ill-prepared in the literature, because there is also a notion called well-prepared, where you make a stronger assumption. In the well-prepared case, you will have this rho naught epsilon minus 1 is like C times epsilon square. We don't assume that. And they also assume a bound on the velocity and also the divergence of the velocity field. That is what is called well-prepared. And here we assume only an ill-prepared data. And what is classical is this result due to Kleinerman and Maida from 1982, and where they have shown that this limit as epsilon going to 0, these compressible Euler equations approximate in some appropriate sense these incompressible Euler equations. So we have the incompressible momentum balance and a divergence condition on the velocity. And this is what is called a singular limit in the literature, because in this limit, you see that the rho disappears because this rho becomes a constant in the limit. In fact, because of this particular relation here, this rho goes to 1, and it is what's called a singular limit because these equations have a mixed hyperbolic elliptic nature, whereas the compressible Euler equations were purely hyperbolic. And one of the aims of our this numerical analysis will be to basically capture this limit at the discrete. Start with the discretization of the compressible Euler system, and you want to send this epsilon to 0, and finally you want to get a discretization of this incompressible limit system. This is one of the major aims we have in mind. And to do that, we start with some energy identities satisfied by this equation. So I introduce some quantities here we call the internal energy, which is defined depending on the value of gamma like this. As when gamma equal to 1, it is rho times log rho, and otherwise it is rho to rho gamma by gamma minus 1. And this is a nice convex function, and it satisfies this relation connecting this psi gamma and p. This will be used in the calculation. And we also need a quantity which is an affine approximation of this psi gamma, which we call the relative internal energy, denoted as pi gamma, which is defined like this. Well, now we go to the energy identities satisfied by the equation, the solutions. So the regular solution, the classical solutions satisfy these identities. The first one is a renormalization identity. That is a balance of, it's not a conservation, it's a balance of this internal energy. And then it also satisfies a positive renormalization identity in terms of this function pi, because pi gamma, there should have been a gamma there, pi gamma. And it also has a kinetic energy because of the motion, and that balance of the kinetic energy is like this. And now what we do is basically we sum this renormalization identity and the kinetic energy identity to get what we have, the entropy inequality. I call this function this E epsilon, which is given as the entropy, which is basically the relative energy. So I don't distinguish between this energy and entropy in this context. And it for classical solutions, we have this additional conservation of this energy, which is satisfied. And this is the one which is we are going to use to get this limit, and also to get some knowledge of the solution in terms of some estimates. Okay. So the goal of this work is to design and analyze an energy stable or entropy stable scheme in a finite volume setting for the Euler system, which is parameterized by the Mach number epsilon. That is our goal. So to achieve this goal, I borrow a framework which is called asymptotic preserving in the literature, that is due to this Chinese-American mathematician Shi Jin in 2000. So basically the idea is like this: you have a singularly perturbed problem, P epsilon. That's a problem which depends on the small parameter epsilon, and we assume that this P epsilon has a limit which we call P0, and we assume this is P0 is well posed as epsilon going to 0. And the question is like this: if you start with a numerical scheme, which let's denote it as P epsilon H, where H is a generic discretization parameter, is called asymptotic preserving. That is, this scheme for the discretization procedure is called asymptotic preserving. If the limit of this P0H, that is the discretization of this limit as you send epsilon to 0 in this P epsilon H, is a consistent approximation of the limit problem P0, and the stability constraints on this discretization parameter H remain independent of epsilon. So that means you have this discrete problem which is discretized with H denoting a discretization parameter, and we assume that this is a consistent discretization of the problem P epsilon. That is, when you send H to go to 0, you recover P epsilon. And the question is, now you send epsilon to 0 in this P epsilon H, you get P0H, and the question is it a consistent approximation of P0? That is, and if you send H to 0 in P0H, do you get P0? Okay, so the question is whether the limit of a discretization is a discretization of the limit. That's a in simple terms? That's a question which we are asking. So if this diagram, if it commutes, we say that this scheme is asymptotic preserving, and we want to get this asymptotic preserving property for the zero Mach number limit. That means we want to start with the discretization of the compressible Euler system, send this epsilon to go to 0, and we want to get a consistent discretization of the limit problem, that is P0, which is the incompressible limit system. And the basic idea, the core of everything is this trick, which is called a stabilization, that is due to some French mathematicians. And the idea is to shift this velocity in the convection, that is here in the mass convection and this momentum convection. You add this term delta U epsilon, and the idea is that this delta U epsilon serves the role of a regularization or a stabilization parameter, and we will choose this delta U epsilon after performing a stability analysis of this system, that is after introducing this shift, and that stability analysis, so basically a posteriori, we get an expression for this delta U epsilon. And the idea is that the stability is very crucial in many other contexts. For example, if you are interested in preserving some stationary solutions, or it also gives you necessary bounds to perform this limit epsilon going to 0. So it actually helps us in so many ways. And this is the system I introduced, the stabilized system. And what I do is I do the same procedure, that is deriving the energy identity satisfied by the stabilized system. I start with the renormalization identity, the positive renormalization identity. And you see the only change here is that instead of U, I have this shifted U, which is sitting there. And it also has the kinetic energy. And finally, we have the energy equation, which is now instead of U, I have this shifted U. And on the right hand side, I have some additional term coming here because of this because we are introducing this delta U epsilon. And what we notice here is something very nice. That is, if I choose this delta U epsilon as proportional to gradient P, then my right hand side will be, because of this minus sign here, will be negative, right? So I can get this, if I integrate now this relation over the domain omega using the, and after using the boundary conditions, we can show that this time derivative of this E epsilon is less than or equal to 0, or this E epsilon is decreased. So I get the stability of this energy by introducing this delta U epsilon. That's the main idea behind this one. So the choice of this delta U epsilon is crucial. It should be proportional to the gradient of the pressure. And then we can achieve the energy decay. So now I introduce the numerical setting. So the basic idea is now we have the stabilization, and which we will also we are going to use it in the numerical set. Okay. So the numerical approximation, we start with the mesh and unknowns. So we use what is called a mat grid, which is a pair ME, which is the grid is called denoted here, and this pair M epsilon, or this ME, has two parts. M is called a primal mesh, and for us it is going to be a collection of rectangles if you are in 2 dimension, or cuboids or parallelepipeds in 3 dimension. And we assume that our domain can be partitioned with the help of this rectangle. So most of the problems we are going to work with Cartesian grids, and this here is going to be the set of edges. So for each primal cell, which we will denote it as a generic K here, the boundary is the union of all edges of this primal cell, basically rectangles or parallelepipeds, and we denote by E int the collection of all interior edges, because once you have a domain and you fill it with rectangles, you have edges which are either sitting on the edges of the boundary of the domain, or else the edges which are sitting inside. So the interior edges, we denote it as EI in those edges which are orthogonal to the ith direction, EI. And EI exterior is basically the collection of all external edges which are basically on the boundary. And this EI is the union of both these internal and external edges. And what we are going to do is this edges we are going to denote by the symbol sigma. So for an internal edge, which will have basically two neighbors, K and L, that is sigma separates the K and L. So we denote it as sigma equal to K by L. And what we are going to do next is introduce another set of these cells, which we will call the dual cells, which are dual to these primal cells, and they are constructed like this. For each phase sigma of a primal cell in the interior, we denote this by d sigma, the associated dual cell, that is defined like this. So if sigma is an interior edge, that is it is inside, it will have two neighbors. So basically we collect one half of K, the left neighbor, and one half of L, the right neighbor, and take the union of this, that forms the dual grid. And if it is at the edge, it is only one side will be there. In that case, we take d sigma K, which is it is on the right side, what is coming in the left. So these dual cells will be full cells if it corresponds to sigma in the interior. If sigma is an external edge, it will be basically half cell. Fine. So these dual cells will also cover this domain omega, and this with the set of all edges of this dual cells, we denote it as P bar of d sigma. And this is the schematic. Basically, in here, what I have is this K, L. These are basically the primal cells, and we are forming the dual cell. So here I have a sigma which separates K and L, and this violet cell here is the dual cell d sigma, and the dual edges, the edges of the dual cell, we denote this by epsilon. So here we have epsilon 1, epsilon 2, epsilon 3, and so on. So these are the edges of the dual cell, and this is the what you call the MAC grid. And what we are going to do is now we are going to basically represent the unknowns of the problem. And so here we assume that a discretization of the domain using a MAC grid is done. That is, we have this M and E. Now I denote by Lm of omega the set of all functions that are piecewise constant on the primal cells. So which I call Lm of omega. Similarly, for each direction, because now the dual cells are going to be, if it is in the previous figure, so here is the d sigma corresponding to a sigma in this direction. Similarly, for this sigma, which is again edge of the primal cell, there will be another dual cell which is sitting like this. Right. So for each direction, I am going to have dual cells, and so for each I, fixed I from 1 to d, I denote this by HEI of omega, which are functions that are piecewise constant on the dual cells, which are in the direction I. And finally, HE is basically the Cartesian product of all these sets, and that will represent the quantities which are piecewise constant on the dual grid. And this is these are some spaces which are for later calculation. It's not very important. So these are function spaces with zero boundary values, like our H10 functions. And so for a function which is on the primal grid, I define what is called a dual average, because the dual cell is composed of 2 or half of a primal cell, which is given like this. So this is the basically averaging over these half cells. I have the dual average. So this is what we call the dual average of a primal function, which is denoted as Q here. Okay. Now this is now the construction of the fluxes. So we are going to discretize the fluxes. So the main idea is to construct the mass flux, and the momentum convection flux is going to be constructed using this mass flux, and the pressure gradient, which is that's the only term which is remaining, because in the Euler system you have two convective fluxes, mass convection, momentum convection, and the pressure gradient. we construct the mass convection flux, and the momentum convection flux will be constructed using the mass flux, and the pressure gradient is going to be a simple center differencing, and that completes our discretization procedure. And here is the how we get the mass flux. So this is what you call an upwind mass flux. So for a function rho, which is piecewise constant on the primal cells, and a velocity which is in HE0, we construct the mass flux through an edge sigma of a primal cell K, that's a notation F sigma K, depending on rho and V, is given like this. So here sigma is K by L. It is an interface separating K and L, and we do an upwinding. That means this V sigma K, that is nothing but the component of the velocity in the ith direction, that is sigma is in EI. We compute the normal component of this velocity. We break that into a positive and negative components, and we do an upwinding. With the positive part, I have the contribution from the left cell, and with the negative part, I have the contribution from the right cell, and that completes the flux. Only thing what is to be specified is that this what is V sigma, how do we define, and how do we define this positive and negative parts, that will come later. So with this construction, what we have is now we go to the momentum convection flux. So the momentum convection flux is, as I said, is constructed like this. It is again an upwind procedure what we do. So a momentum convection flux, depending on these three unknowns, rho, V and U, is given by this expression here. And this F epsilon sigma is basically the dual flux through a dual edge epsilon of the dual cell D sigma. And this F epsilon sigma is going to be a linear combination of the primal mass fluxes, because if I have a dual edge, I will have two primal edges on the either side of this dual edge, and we simply take an average of these two primal fluxes to get the dual flux. And then to introduce an upwind bias, we do this upwind choice of the velocity, because the dual momentum convection flux is now rho U tensor U. It's like rho U square, rho UV, and so on. That is why I still have this upwind part there. And to do this upwinding, what we do is simply like this. So this upwind velocity on the dual edge, because this is now at the dual edge, whereas my U is discretized on the edges of the primal cells, which are sigmas. So I have this flux which is computed by taking the average, and depending on the sign of this dual mass flux, I take U sigma or U sigma prime, depending on which side the sigma is sitting. Okay, like the standard upwind procedure. So that completes the construction of the convection fluxes, mass convection, and the momentum convection. Now what is left is to define the pressure gradient, and that we do a simple centered choice. So for an interface separating K and L, we take this QL minus QK, and these are usual finite difference these factors, and that gives you a derivative in the ith direction. And the set of all these you collect all the derivatives, that gives you the gradient operator in the discrete cells. Similarly, so this gradient, what is important is that these gradients are defined at the primal edges, so they are basically sitting at the dual edge. That is why it is this characteristic function of this D sigma coming in this representation. Similarly, we define the discrete divergence operator. Divergence is centered, so divergence is sitting at the center of the primal cells, which is given like this, and this divergence is nothing but the usual way. So we have the velocities, if it is V, any function, the normal component of that, and you take the sum, and finally divide by the measure of K, that gives you the divergence, which is now sitting at the center of the primal cells. Very good. And what is very crucial for us is this gradient divergence duality in the discrete sense. the gradient and the divergence, which are defined like this, satisfy this duality relation, because this is to be used to cancel out so many terms. By using this duality, we cancel the terms when we finally do the energy stability. And one more result which I recall here is this inf-sub stability, which is stability result satisfied by the Mach grid. And what is the importance of this result is that this result basically helps us to estimate the norm of the L2 norm of the pressure in terms of the L2 norm of the gradient. So by doing this energy stability, we will get a control on the gradient of the pressure, and using the gradient of the pressure, we control the norm of this. Basically, it has to be a zero mean. That's why this M of P is the average of P. So this we have to subtract the mean to get the zero mean pressure, and the norm of that can be estimated using this identity, and that is the result of this inf-sub stability, the usual inf-sub condition. Very good. Now I present the scheme, and this is the final numerical scheme, which is semi-implicit. So here is the discrete mass conservation, and here is the discrete momentum conservation. So you can see that this is sitting at K here. That means we are discretizing the rho at in the primal cells, whereas this momentum is now for the dual cell. So each component of this velocity is now in a dual cell. So for if in the ith direction, I have this d sigma. So ith component of the velocity that is sitting there. And here is the momentum convection flux, which we have introduced. And here is the pressure gradient. And if you notice here, a few things are to be noted. One is in the mass convection flux, I have a rho n plus 1 sitting. And this is a nonlinear relation. So this is implicit and it is nonlinear in rho n plus 1. If you know rho n plus 1 from the first update, then this can be updated explicitly, because this you can obtain and this also you can obtain. So everything is now done. This second relation, the momentum convection, can be evaluated explicitly, provided this first one you compute. So the scheme has basically one implicit step, and this is an explicit step, though it looks like an implicit step. Right. Now I make the choice of this velocity, stabilized velocity, which we denote as V. U sigma is the actual fluid velocity, and motivated by that first relation, that is this stabilization delta U is proportional to the pressure gradient. We take that as eta delta T by epsilon square times a discrete pressure gradient. This delta T is basically to make this term disappear when we refine the mesh, so that it doesn't make a quadratic pressure, because this is an extra term, artificial term, which we are introducing just to get the stability, and that will so provided this remains this discrete pressure gradient by epsilon square remains bounded, that we will get it later. We can make this term disappear if we refine the mesh, that is when delta T goes to 0. So this is now the choice of the stabilized velocity, and now I introduce this positive and negative parts of this V sigma, and that cannot be defined in the usual way, because this delta U, that is this term here, the negative part of that and the positive part of the velocity, and since it is a minus here, so this V sigma plus is always non-negative and this is always negative. So that is the way we define the positive and negative parts. So this basically completes the construction of the scheme, and the first result is about the existence of a solution. Since the mass conservation is implicit in rho n plus 1, what we do is we treat that as a nonlinear relation in rho n plus 1, and we use some classical topological degree theory arguments to show that it has a solution and it also has a positive solution. So we show the positivity of rho at n plus 1, provided rho n is positive, using this topological degree theory argument, and that also gives you the existence of a solution, because that is the only thing which has to be done. Once rho n plus 1 is known, this un plus 1 is known explicitly. So there is nothing to be proven about the existence. That is standard. So this rho n plus 1 and the positivity of this, we prove it using this degree theory argument. And that is the what structure preserving property we had it in mind, that we achieve like this. The next one is we propose this energy stability. So towards that end, I derive a mass balance on the dual cells, that is simply by averaging the mass balance on the primal cells or the dual cells. And then this is about the how we initialize the data. So given the initial data rho naught and u naught, we average rho naught over the primal cells to get these approximations, and we also average the velocity components in each direction to get this u sigma naught. So this is the initialization procedure. And next we do this energy balance, energy identities satisfied by the solutions. So first is the discrete form of this renormalization identity. We derive this, it follows by calculations, and using some convexity of these functions, etc., we can get this discrete form of the renormalization. And because this psi gamma being convex, we can easily show that this Rk, which is the remainder term, is always non-negative without any conditions. And the next is the discrete version of the positive renormalization that also follows from this. And then we go to the kinetic energy part, and the trouble there is that the remainder term which comes there has now a mixed nature, because this term is negative whereas this term is positive. So we cannot say whether it will always be non-negative or not. So we have to basically analyze these terms once more. So what we do is, so here this, we don't know the sign of that. So what we do is we estimate this term here, which is the first term, and use some convex function arguments and so on, and finally arrive at this inequality here. So this is the total energy balance. So I have the positive renormalization, this pi gamma, the difference of that at times n plus 1 and n, and here is the difference between the kinetic energy, and then I have this extra term which comes because of the stabilization term, and this is the total energy. So it is summed now over this k, and the kinetic energy is summed over the dual cells, and I have this extra term that which has to be controlled. So we need to put conditions so that we know the sign of this term, and that is where these conditions come. So here you can clearly see this eta has to be greater than or equal to this one, so that on the once I push it to the right hand side, it is negative term. And to get this less than or equal to, what I do is basically estimating the extra terms coming from the kinetic energy as in the previous slide, and that requires a condition which is again a condition on the time step. So basically we have two conditions. One is a condition on the stabilization parameter eta, which has to be greater than or equal to this one. Only thing is it is implicit because it involves the rho at n plus 1, which we do not know. So in practice, we have to have a workaround how to impose it. And second one is a condition which involves the flux, and this flux also at n plus 1. So that is also implicit. And this we, in practice, we enforce it only at n. That's what, as if it is available. So every time we do it at n and compute a time step and use it again the next step and so on. So that's the way we actually compute it. Now, basically now we go to a consistency of this scheme. So what we want to prove is that this numerical scheme, we want to show that this numerical scheme is consistent with the weak formulation of the Euler system. So to do that, we restrict ourselves to a one-dimensional situation. So here these Ks are basically intervals, and these dual cells are also basically intervals. And so here is the same scheme which is written in one dimension. And what I do is we have these VV norms. So these VV norms for the primal cells and VV norm for functions defined on the dual cells in space. And We also have the BV norms in time, also in the primal cells and the dual cells. And here is the result. So the result basically says that this weak consistency is like the usual Lax-Wendorf cells. So we have a sequence of discretizations so that the discretizations and time steps, so that the time steps and this the diameter of this cell, this discretization, this cells, it goes to 0. And we have a sequence of numerical solutions, and that is guaranteed now because the existence is proved, and corresponding to a sequence of initial data which is assumed to be bounded. And we also assume now, this is an assumption, that these sequence of numerical solutions, they satisfy. So we assume this L infinity bound on the numerical solution, and we also assume that this BV bounds, we assume that this BV norms in space, this is bounded, and we also assume one more, this BV norm in time for the rho component is also bounded. And this assumption is precisely because of the stabilization which involves the quantity at n+1. So with this assumption, these are basically assumptions which we make, and this is about what we call the mesh regularity. That is this a ratio of this time step to the minimum, the smallest cell here, and that ratio is going to 0. This basically avoids that you don't have cells which are like something oblique. So it's this the cells remain nice and so on. So once we have these assumptions, if you have now the sequence of numerical solutions, if they converge, then that limit must be a weak solution of the Euler system is the result. So it's in the sense of Lax-Wendorf. We have some boundedness assumptions, and if the sequence of numerical solutions converge, then the limit must be a weak solution. So here is one consistency analysis. We also have another consistency which is done in a more general setting. So here we don't make the previous assumptions. The only things we have is these conditions on the time step and the stabilization parameter, so that this global entropy inequality, the energy inequality is satisfied. And we also assume that this scheme is consistent. Then we can show that you have this weak convergence in the sense of measures here. So you can show that this sequence of solutions converge to some Young measures. The limit is given by this by a Young measure, and that we call a dissipative measure value solution. This is also done in detail by Ujjwal in stochastic Euler setting and so on. So this result also we have shown. It's a so with less assumptions here, and here is a tool which we use later, what is called a K-convergence. This is about, because since the limit is a measure which cannot be seen in a computer in numerically, so here is what we call the K-convergence or Komlov convergence, that shows that if you take an average of these numerical solutions. So here this averaging is M is now for the sequence of discretization. So we basically refine the these grids and take the average of the solutions, and that has a strong convergence of this Cesaro means that is that can be shown. And we also similar results which we can obtain as the what we call the Wasserstein distance, and also these deviations in L1 norm. So these are strong convergence results which we can prove, and this can be visualized because it is now a strong convergence, whereas the weak convergence we cannot visualize numerically. So these are the two consistency formulations we have performed, and now I go to this last part, which is the consistency with this low Mach number. Now here we want to now so we fix the discretization, and we want to send the limit epsilon going to 0 in the scheme. And we want to show that the limit of this discretization is now a discretization of the incompressible limit system, the incompressible Euler equations. And we prove it in two steps. One, first, we prove the convergence of this rho epsilon, the discrete rho epsilon. And that comes very easily because of the energy inequality we have because we have a control on this quantity pi gamma, which is a convex function, and using some convexity property, we can easily show that this rho epsilon for each k converge to 1. That we can easily show. But what is to be done, some extra work which is to be done is about the pressure, because we have a stiff term 1 by epsilon square in front of the pressure gradient. And what we do is here we use the in-soup stability. So if you remember, we had this term, I just go back to that energy term here. Yeah, so here, once we choose this eta there, basically you are going to get a bound on this gradient of P by epsilon square in the L2 now. So we can bound the L2 norm of the gradient of P, and now the in-soup, we exploit the in-soup and get the bound on the L2 norm of the pressure, and that is what is this lemma is saying here. Yeah. So using this in-soup stability, we show that this zero mean pressure, that is, we subtract the mean value, and this zero mean pressure remains bounded independent of epsilon. So you can now extract a subsequence which converge. And now the only thing which is remaining is to pass to the limit as epsilon going to 0 in the numerical scheme. It's now pointwise convergence, because rho epsilons are converging to 1 for each k, and this zero mean, this pressure term is also in that also as a convergence subsequence. So at least by taking a subsequence, we can prove that the scheme has a limit, and that is the result here. So I have now a sequence of epsilons which converge to 0, and I take the corresponding sequence of numerical solutions corresponding to an ill-prepared initial data. Then we show that this rho k converge to 1 in L infinity 0t, L gamma, and this tuple, this uk pi k, that is the velocity, and this zero mean pressure, it has a limit u pi in any discrete norm, and u pi is a solution of this system. And if you see here, this is nothing but the incompressible equations, because we have a divergence, and here it is the incompressible momentum balance. The only thing is that this is again a stabilized incompressible, and to recover again a consistency, you can again take the limit as delta t going to 0 and exploit the energy stability, because this will also have a kinetic energy. So with that, we can show this is also a consistent discretization of the incompressible limit. So basically, we have shown that the limiting scheme is a stabilized scheme for the incompressible limit Euler equations. So this is basically the summary of this. So we have shown three things. One is the positivity of rho, and that came from the degree theory proving the existence. And then we had under some conditions, we obtained the energy stability of the numerical solution. And finally, we have also performed this limit as epsilon going to 0, the zero Mach number limit, and we get a consistent discretization of the limit system. Okay. So this is these are the three things we wanted to achieve. And now I show you some computational results. So here, so we test this numerical scheme for different values of epsilon. So the convention is that when epsilon equal to 1, it is the compressible Euler equation. So we are solving the Euler system. So you can expect the usual discontinuities like shocks or contacts, expansions in the solution. So here, this is a test problem which has basically a different Riemann problem. So the solution has several discontinuities. It's a piecewise constant solution, and pressure law is given to be like this, and we have these the interval is divided into 200 mesh points, and the boundary conditions are periodic, and it's a final time. And what is interesting is that we compute this for different values of epsilon, something very close to 1, and we step by step we reduce and take something very small here, so that you expect the solution to be like an incompressible. And here is the Okay, this is another which I will come to that. So here is the profile. So the first one, this is the density corresponding to 0.8. So you can see the solution has discontinuities, and as you reduce epsilon, these discontinuities smoothen, and when this in the next one I should have, when epsilon is very small, actually the deviation from 1, your rho is almost 1, because the solution has converged to this, rho has converged to 1, and that we can capture it corresponding to epsilon equal to this small value. And here is the velocity component that also has a similar behavior. And this test problem is what is called an extreme Riemann problem. So here is basically a constant density and the velocities are opposite sign. So this gas is going to expand, it's going to be a rarefaction, and so it's going in opposite direction. So you expect a vacuum to form at the middle, and that is precisely what we are going to see. And this is not a test for the low Mach number or anything. We are simply setting epsilon equal to 1 here, and I have the numerical result here. So you see here, this is so this density is almost touching 0, but still the code works because of the positivity preserving property of the scheme, and that is what we wanted to demonstrate, that the scheme has a positivity preserving by taking this extreme Riemann configuration. And this is the to show this DMV convergence. So here what we do is basically we compute the for the density the usual L1 norm errors, and these are the errors in the deviation, that Wasserstein distance and so on. And we see that these L1 norms, they don't decrease because of this DMV convergence, whereas the other norms they decrease as you refine the mesh. Basically, it shows the DMV convergence. So this is just to show you this that is strong convergence, K convergence result. We can implement it numerically and show these convergences here. And finally, I go to some vortex as a 2D test problem. So here it's a vortex which is centered at 0.5, 0.5. Domain is 0, 1 cross 0, 1. This is the initial data, and these are some configurations here. And what is the purpose of this is to control this epsilon and to measure how much is the dissipation present in the scheme as a function of rho here. So we are going to vary this rho for everything, and we compute this Mach number and measure this as a function of rho and measure the dissipation. So we are going to vary rho from 10 to the minus 1 to a very small value, 10 to the power of minus 6, and the computations are performed for t equal to 5/3. This is basically one period of this vortex. So it completes, it's a standing vortex which is rotating. So it completes one rotation, one period of rotation. And here we have the result. So here this is the cross section of the vorticity after one period, and we have plotted this for different values of epsilon. And you see these are not distinguishable. So that means the dissipation of the scheme, it performs uniformly in epsilon. And here is the what you call the relative kinetic energy. At time t equal to 0, the relative kinetic energy is 1. So we are dividing the kinetic energy at any time by the relative this kinetic energy at time t equal to 0 to get the relative kinetic energy, and we plot it for different epsilon as a function of t in this interval. And you see for every epsilon it is almost the same. It is not distinguishable. And the next I show you the pseudo color plot of this vortex. So here is the Mach number plot at time t equal to 0, and we plot the same for different epsilon after one period, and you see these plots are all again identical. So this basically shows that the dissipation of the scheme remains independent of epsilon, and that is one of this, because this is a very demanding test problem in the numerical community, basically to test the dissipation of the scheme, and our scheme performs very well in this one. And the next test problem is what you call an explosion problem. It's a Riemann problem. So we perform this for two different values of epsilon. One is epsilon equal to 1. Other one we will choose a very small epsilon. So rho is a piecewise constant. So it is the higher density in inside the circle. Outside it is just 1, and the velocities are initialized like this. And we compute this problem on a 100 by 100 grid and with the periodic boundary conditions. And here is the numerical solution, which you can see here. So you have a circular shock wave which is going out, followed by an expansion. And here is the cross section. Here, this is the 3D plot. Here is the cross section of this. And we have compared the result because it's a radially symmetric problem. We have compared the result with the quasi one-dimensional solution of the Euler equation that is used as the reference solution. And you see a very good agreement between the numerical solution and other one is 1D on a very fine mesh, because it's a quasi one-dimensional, whereas the dots here are from the 2D simulation. And we have made these plots for 3 values of the time and corresponding to epsilon equal to 1. So you see the discontinuity, and like in the one-dimensional Riemann problem, in 2D also, the scheme performs very well when epsilon equal to 1. And this is again a cross section which we have. And here is the other interesting part, that is corresponding to a small value of epsilon. It should be given there. No, sorry, it is. Sorry. This is for epsilon equal to 10 to the power of -4. And what we have plotted is basically rho minus 1. And you see here the error is of 10 to the power of -9. And here is the divergence, which is also flat and 0 there. So you are getting a divergence free velocity field and a constant density corresponding to this small value of epsilon. That means the scheme can capture the incompressible behavior corresponding to small value of epsilon. And when epsilon equal to 1, it produces the compressible behavior with the discontinuities like shocks and expansions and so on. And that is basically these 2 extreme regimes, it works very well. And this test problem is a test problem from the incompressible Euler system. We have this rho, we fix it equal to 1, and the velocity is now like a shear which is initialized. And we test it in an incompressible regime. That is whether the scheme performs well in for a very small value of epsilon. We set epsilon equal to 10 to the -6, and we have the configuration. And what we do is we basically measure this for the density and this deviation of the density as a function of rho and the L2 norm. And we can see that this, when epsilon reduces to 10 to the -6, the error is like 10 to the power of -12. And maybe there is also a plot of this thing. So one is computed using the compressible solver, and other one is computed using the using an incompressible solver, and they are almost the same. So that the numerical solutions show a very good agreement, and that at epsilon equal to 10 to the -6 is almost like an incompressible solver now. Okay, so with this I conclude this. So we have designed an asymptotic preserving scheme. That means we have shown that the limit of the epsilon going to 0 limit of the scheme is a consistent discretization of the incompressible limit. That is the limit of the continuous system that we have shown. And the key to energy, this was achieved using the energy stability. And the key to energy stability is stabilization in the velocity, which is introduced. And the bounds given by the energy identity are used to prove the incompressible limit, and it also gives us the bounded numerical solution. And the consistency, we have shown the consistency with the incompressible limit in the epsilon going to 0 limit, and for fixed epsilon, as you refine the mesh in 2 cents, we have shown the consistency in the last Van der Rohe sense. And yeah, so that is all. These are some references. So this is where the stabilization technique can be found. Is Arnaud Duran, Ronco Villa, and so on. And this is about some preliminaries on the finite volume. And this was something on the staggered grid. And yeah, with that I stop.
So, any questions?
Thank you for this nice presentation. So I have just a small question about this equation to define this delta V.
Yeah.
And or V.
Yes.
And how you find it seems to be something related to the fact that the let's say, if you take the compressible fluid and then look at the equation on the pressure,
yeah,
then you have something like that link, let's say, the fluctuation of velocity and 1/square root of the Mach number grad of P.
Yeah.
And it seems that that is what you are using.
That's what we are using.
But it came here afterward by numerical. You cannot do it before doing the numerical.
No, we do the thing at the continuous level.
Yeah.
So we do this energy stability of this stabilized system at the continuous level. That gives you this expression. And the stabilization has to be gradient P by epsilon. If there is no epsilon, it's a proportional gradient P.
Okay. So there was. It is not shown in the presentation, but
no, it was there in the. I showed the continuous case. There also we get this delta U as.
Okay, so from the delta U, from the continuous case, you have
we do that numerically.
And then you transform in numerically.
Okay, exactly. Discrete pressure. And the interesting thing is that this gives you an L2 bound on the gradient P, and that was crucial to pass to the limit as epsilon going to 0.
Any other question?
So actually, I have a related question.
Yes.
I do not follow what's the motivation behind, I mean, in terms of, let's say, physical motivation, why you add this stabilization delta times?
Okay, so two things. One is this gives you the energy stability.
No, but how do you derive? Is there a physical meaningful model which actually can derive? Like
Yeah, so what we did is at the continuous level, so the Euler system, the velocities, we introduced this shift.
Yeah.
And we derive the total energy.
Yeah, sure. But how do you, is there any change in, let's say, stress of your?
No, it's a.
How do you derive?
No, it's a compressible inviscid.
But how do you derive? I mean, why that term is popping on?
This delta U.
Yeah.
No, we introduced that.
Sure, but is there any physical motivation?
Yeah, so then what happens is once you derive the energy, the right hand side, you get a term like delta U dot gradient P minus with a minus.
Yeah, but that's for a mathematical reason, right?
Yeah.
I mean, just to give you some parallel. So if you have Euler, if you have Navier-Stokes,
right.
Of course, both systems are physically motivated and you can derive them separately.
Yeah.
So my question is that with new delta U, is this a physical model you can derive independently? I mean, otherwise it looks like
so the first time it was used in this what we call that AUSM finite volume. So this was used by some numerical community. But this actually has some structure because it will give you some necessary bounds like L2 bound of gradient P. That extra remainder term which comes when you estimate the energy, you get the L2 norm of the pressure gradient.
Yeah, but isn't it tailor-made? Does it really have some meaning?
It's basically introducing some dissipation.
Yeah, it's a sort of a dissipation.
It's degenerate dissipation. What kind of dissipation you are getting? Can you please go back to
that one? Yeah.
So is it needed to prove the positivity of rho also?
The positivity of rho will follow otherwise also. So
without delta U, you can show this.
So how will I go back? I don't know whether I can. At the continuous level, if I.
Yeah, it's the beginning, right?
Yeah. Before the numerics. Yeah, so here it is. So I write that. So here is yes. So this we introduce this shift in
You
the,
see the dissipation you are talking about, it's a degenerate dissipation, right? So it's not clear that will regularize the solution itself. It's divergence rho times U epsilon. I don't see why you expect the solution to be smooth if you add that stabilization.
no, I mean, we just call it basically, yeah, I mean, we call it a stabilization, but in the literature, they call it some potential regularization or something of that sort. That's
Yeah,
what,
in which sense it is regularizing, so that's.
Let's say if you replace that delta by gradient of P is just gradient of rho.
yeah, so you
It's gradient of rho.
basically
If you-
estimate the,
you know.
yeah, see,
Yeah, but then it is degenerate, right? U is also involved.
No, if you gradient, if you, U is there,
Delta
but
U epsilon, okay.
delta
Yeah.
epsilon is proportional to gradient of rho.
gradient of,
And then it gives you a diffusion with a non-constant, non.
so it basically makes this
Yeah, but
energy
that's what I
decay.
mean, that it is like degenerate in the sense P can degenerate. I mean, you have power law, right? Low power
Yeah,
law.
yeah.
Of course, near vacuum, you will be in trouble. It can
If
degenerate.
gamma is one,
Yeah, near
Yeah,
vacuum.
gamma
it
is
will-
greater than one.
Yeah, so in the computations, we basically took gamma greater than 1. Gamma
This
equal
is
to
very
1.
specific to some. modules.
Yeah, like
Not
most of the
everything.
problems are done with gamma equal to 1.4.
Any other question? So at the theoretical level, does this regularization like prevent shock formation? Or like is the solution also differential?
No, so see, no, so because what it does is only introduces this, it doesn't do any smoothing or anything. It basically causes the energy decay. And
Regularization is in terms of the L2 stability.
not exactly that also. This regularization may not be the right word to use. Maybe we should use some other terminology here. So the idea is to get this energy bound so that you have a bounded numerical solution. And that would be. So that was the main idea, to get the energy stability of the numerical solutions. But then as a byproduct, we get the this bound of gradient P by epsilon square, which was needed to pass to the limit.
Then coming to this expression,
Yeah.
it is not in conservative form. Why? Because you have this U epsilon additional.
Where right
No,
hand.
the first line. Yeah, there. You have then this term.
No, but this is now like a new velocity. Right, this is the energy flux.
But it's not a conservative.
It
form.
is, so this, okay, this divergence is for the whole thing.
Ah, okay, so, okay.
For the whole thing.
I understand.
Whole thing, sure, yeah. Sure.
Okay, so there's no more question, we can stop and there's some snacks. Also, you can ask more questions there. So thank you.